All right, let's do this. All right, so we're going to start in on our next chapter here, and the focus of this chapter is ethers and epoxides. Okay, so first of all, an ether is another oxygen-containing functional group, but that oxygen is necessarily sandwiched between two carbon atoms, right? So our alcohol necessarily had that hydroxyl group, that OH group. An ether is when that oxygen, both of those bonds on that oxygen are to carbons. Right, so an ether necessarily has that carbon, oxygen, carbon bond going on. All right, and as the title implies, we're also going to talk about epoxides. Epoxides are actually just a type of ether. So again, we have our oxygen bound to two carbon atoms, but it is a very special type of ether where that oxygen and those two carbon atoms are forced into this three-member ring here. All right, so again, technically an ether because that oxygen is bound to two carbons, but we're going to put them in a separate category in our brain because these epoxides are way more reactive than other ethers because of this little triangle. Carbon atoms don't like being forced into this 60-degree bond angle here. So we're going to see these epoxides are very, very reactive compared to other ethers. We're going to focus today on ethers exclusively, and then we'll move over to epoxides next lecture. Ethers turn out to be kind of boring. They don't have a terribly large, they're not terribly reactive functional groups. And so instead, ethers are most commonly used in the lab as nonpolar solvents. All right, if we want to remind ourselves, last class, or rather last week, we made this kind of little polarity spectrum here when we talked about alcohols. We said that alcohols were relatively polar organic functional groups. And so they're used as relatively polar solvents, right? And we sort of updated our way of thinking about the world. It's not just black and white, polar, non-polar, but rather there's this little bit of a spectrum. All the way on that polar end of our spectrum, our most polar solvent would be water. Alcohols have that OH group, so they're still able to hydrogen bond, but they got a bunch of carbons and hydrogens on there. So they're not quite as polar, but they're over here. And then we said all the way at the extreme other end would be our alkanes. Those are our non-polar solvents. Well, ethers kind of sit in the middle here. All right? More towards that non-polar end, I'll say. They're not quite as non-polar as our alkanes are because they have that oxygen. That oxygen has those lone pairs, but it can't do any sort of hydrogen bonding because there's no OH group. All right, so these ethers kind of sit more towards the non-polar end of our solvent spectrum here. Cool, all right, so as with any functional group here, the first thing that we're going to learn how to do is how to name these molecules. All right, so our nomenclature of ethers. Okay. One thing that we're going to just kind of note right off the bat here that's going to make these ethers a little bit different than the functional groups that we've introduced before, right? We introduced alkenes and alcohols, and we always had this functional group part of our parent chain that we prioritized. Ethers are kind of weird. They're much more like alkyl halides, the chloro groups and the bromo groups. They are considered substituents in our naming. So they're not going to go in the back half of the name. They're going to go in the front half of the name, like our chloros or our bromos did. All right, so let's get a good example here. Okay, ethers have this like IUPAC naming scheme here that we're going to use, but we're also going to talk first about the common names of ethers, because it's a little bit easier. All right, so for our ethers, we'll have both like a common and an IUPAC name. The common names are pretty straightforward though. You're going to chop at that oxygen. Okay, so I'm going to look here and I'm going to go, hiya, chop this molecule in half. All right, it's got these 2 carbon chains on either side, and we're going to name those carbon chains just based on how many carbons there are. So in this case, on the left-hand side, there are 2 carbons, so that would be an ethyl group. And on the right-hand side, what do we got? For 3 carbons, a propyl group. So we're going to chop at our oxygen. We're going to name our alkyl groups. And then we're going to assemble those alkyl groups in alphabetical order, followed by the word ether. All right, so in this case here, with my ethyl group and my propyl group, I'm going to assemble those 2 in alphabetical order. So this becomes ethyl, propyl, ether. Okay? Cool. All right, let's do another one for practice here.
Is it all one word or something?
There are actually spaces between them, yeah. For our common names, very rarely with our IUPAC system do you have spaces in the name, but for our common names, we do have spaces between each of those words.
I thought you said that the ether would be in the front.
No, followed by the word ether. So ether at the very end. Cool. All right, so everybody take a second. Give me the common name of this thing here. All right, I'm going to chop this thing at this oxygen. I'm going to look on the left. We have 4 carbons, so that would be a butyl group. I'm going to look on the right. We have 5 carbons, so that would be a pentyl group. And then I'm going to assemble these in alphabetical order. So butyl, pentyl, followed by the word ether. Butyl, pentyl, ether. All right, so we can name these ethers according to their common names or our IUPAC names. You'll note that, or we could just note here that our common names, they only kind of work for our most simple ethers, right? As soon as there are multiple branch points going on or any other substituents, a chloro group, all of a sudden these common names go out the window, right? So it only really works for our straight chain ethers, which turns out to be the most common, all right? There's not a lot of crazy ethers that you'll encounter in the wild because, again, they're kind of boring functional groups. They're typically just used as solvents. But nonetheless, don't worry, the IUPAC has a way to name any and all ethers that you might stumble upon. All right, so let's take that same ethyl propyl ether as our example. But again, now we're going to lay out our IUPAC naming scheme. All right, so this is our normal four-step naming process here, where first we need to find our parent chain. All right, that's typically that longest continuous set of carbons, but for ethers, again, we kind of have this weird situation where we have a carbon chain on either side. All right, so we're actually going to play a very similar game to what we just did. We're going to chop this thing at our oxygen, and then we're going to ask which side is going to be our parent chain. All right, the one with more carbons is always your parent chain. So again, I'm going to chop here. On the one side, I have 2 carbons. On the other side, I have 3 carbons. So what's my parent chain, left or right? The right-hand side with the more carbons. All right, so for our IUPAC, again, we're going to chop at our oxygen. The longer chain is our parent. All right, and like we said, ethers, there is nothing special about them in the world of nomenclature. They're just going to sit out front like a substituent. So our parent chain for an ether is going to be named just like a regular alkane with that ANE ending. All right, so my 3-carbon parent chain here would be what? Propane. And that is my parent. So the other part, the ether part, is going to sit out front here. Okay? So now when we get to substituents, this is how we're going to deal with our ethers. Okay, for your ether substituent, it's the number of carbons plus that suffix oxy. All right, so if we have 2 carbons here, again, my substituent is going to be this whole thing right here, including this oxygen. Right? So it's not just an ethyl group with only carbons, it's got that oxygen as well, so this is an F-oxy group. All right, we got to number our parent chain just like we always do. We're not going to prioritize this ether group because it's not a functional group, it's just a substituent, but we always want that lowest number in the name. And then we're going to assemble our name by putting our substituents in alphabetical order. All right, so again, I'm going to number my parent chain. I want that lowest number in the name, so that ethoxy group is going to be located on carbon 1. So this is 1 ethoxy propane, all run together, all one word. All right, so unlike the other functional groups that we've been learning about, our alcohols, our alkenes, we don't have a suffix for our ethers. We're going to build that into the front half of our name. They're considered substituents in the IUPAC naming scheme. All right, so let's do a few more examples here. Let's just take that same butyl pentyl ether. I want you all to give me the IUPAC name for this molecule here. We did the common name, now we need the IUPAC name. All right, and then we're going to do this next example here. This one you won't have a common name for. We don't have a common name for this chain over here, all right? But you should be able to give me the IUPAC name for this molecule. Everybody take a second and work through these two examples here. So for this first one, my parent chain is going to be this longer fragment with its 5 carbons. We don't have any special ending because this is an ether, so my parent chain here is just my pentane. My ether substituent is these 4 carbons and that ether oxygen. We're going to indicate the number of carbons in this ether group using that same set of prefixes we always use, so but, but it's not going to be a butyl group, it's a butoxy group. Okay, and we need to indicate where this butoxy group is connected to our parent chain. We want it on the lowest number possible, so we're going to put it on carbon 1. So this becomes 1-butoxypentane. All one word. All right, my 1 is my locant of where that butoxy group is. That ether group is that butoxy, and my parent chain is the pentane. Okay. Again, this one we can't do a common name for. We don't know what this thing would be called in terms of our common name because it's connected to a different carbon. If we chop here, which half is our parent chain, left or right? The right-hand side has more carbons. Whoops. All right, so these 1, 2, 3, 4, 5, 6 carbons are our parent chain here. All right. One of the common mistakes that people make when they're trying to do ether nomenclature is they always want to put this oxygen on carbon 1. That's not going to be the case. It's in the middle of this molecule here, right? So I'm going to still do what I always do for my parent chain, the longest continuous set of carbons. And so this ether group here is not located on carbon 1, but on carbon 3 of this 6-carbon parent chain here. Okay. What would we call this 3-carbon ether group here? Propoxy. All right, so my IUPAC name here is 3-propoxy hexane. All right, my parent chain, my longest continuous set of carbons is that hexane, and I have my ether group that's located on carbon 3. All right, let's do one more. All right, so clearly being super creative here, which half is our parent chain, left or right? On the right-hand side. It's not always the right-hand side, all right? I've just been very not creative with the way I've been laying these out, all right? But yes, we got more carbons on the right-hand side. So these 1, 2, 3, 4 carbons are my parent chain here, okay? This molecule has 2 substituents, one of which we would have introduced way long ago. This group right here we call a chloro group. And now we have our new substituent, our ether substituent with just 1 carbon. So this would be a methoxy group. All right, we got to put both of these into our name here. All right, now we're going to number our parent chain. 1, 2, 3, 4. Or I can go the other way. 1, 2, 3, 4. Which one of these is going to be correct? Blue or orange? Blue. Orange. All right. So It's been a minute, all right? We want the lowest possible numbers in our name. So let's just list what we would do if we picked our blue numbering scheme. That would be a 2 and a 4 in our name. If we go and we pick the orange numbering scheme, that's a 1 and a 3 in our name, all right? Let's not get confused. This is not a functional group. There is nothing special about this methoxy group. It doesn't take priority. It doesn't have those same sort of priority rules that our functional groups do. It is just a normal substituent counted just the same as that chloro group, right? Nothing special over that. We just want our lowest numbers in the name. So indeed, hopefully we can see that our orange will give us the lowest number in the name. And when we put this together, we're going to assemble it in alphabetical order. All right, so that means that that 1 chloro comes before that 3 methoxy alphabetically. So 1 chloro, 3 methoxy butane. Just rolls off the tongue. Okay? Cool. So, again, we're going to make a note. Nothing special about those ether substituents. Whether it was a chloro group or another ethyl group, another alkyl group, right? We're just going to make sure we got the lowest number in our name, and we're going to assemble those substituents in alphabetical order when we put everything together here. All right. Cool. So we're going to talk about reactions of ethers. And again, there's not really all that many. They're kind of boring functional groups. That's why they're great solvents, is they're not terribly reactive. All right. But we do have one way to make ethers. And we've actually kind of already seen this here using our substitution of alkyl halides. So let's just call this ether reactions. We can even say more specifically, preparation of ethers. All right, how do we make them? Okay, and again, we've seen these reactions before. These are just substitutions of alkyl halides. All right, and there's one super efficient way to do this in terms of what you choose as your nucleophile and what you choose as your alkyl halide. It's named after a dude. We call this the Williamson ether synthesis. All right, so what we're going to do is we're going to take an alcohol. And we're going to turn it into a really good nucleophile by treating it with something called sodium hydride. Sodium hydride is just a strong base, but it's a strong base that's like specifically used, when you see it in the wild, it's specifically used for this purpose of deprotonating these alcohols. This hydrogen right here is actually pretty hard to remove. What you would consider a strong base in general chemistry, like a hydroxide, sodium hydroxide, is not a strong enough base to remove a hydrogen from an alcohol. You need to use something even stronger than that. And so the go-to that they use here is this sodium hydride. It's going to be a strong base. Whoops. And it's going to remove that OH hydrogen. All right, so what happens in step 1 of this reaction is we remove that hydrogen, and we create these really good nucleophiles here, these oxygens that have these negative charges. All right, one of the reasons that sodium hydride is preferred is there's no chance for this reaction to go back in the opposite direction, because that hydride hydrogen reacts with that OH hydrogen, and that goes flying off as hydrogen gas, right? So you don't have to worry about any sort of reversibility of this reaction. That hydrogen bubbles off and it leaves. Okay? These things here, we've seen these a bunch before. We've used them. We haven't really called them anything. These are what are called alkoxide ions, right? Hydroxide would just be OH minus. An alkoxide means that there's some alkyl group on there. There's carbons and hydrogens. All right, and again, these things are our good nucleophiles. So if we turn around and we react them with our alkyl halide, so for example, this guy here, we're going to get a substitution reaction to produce our ether. All right, and I know everybody's like been super paying attention, so they're like, wait a minute, that alkoxide is a strong nucleophile and a strong base. So don't you have some elimination product in there as well? Yes, we do, all right? But we're not worried about that. We're specifically trying to synthesize this ether. So we're going to tune our conditions and then do some chromatography or something after that to get rid of that alkene, right? We specifically want that ether there. Bottom line, don't worry about the competition going on here. We're specifically talking about this substitution reaction. All right, and again, this would be a second step in our reaction. So first is treating it with that sodium hydride. That produces our good nucleophile, our alkoxide ion. And then we're going to add in that alkyl halide to get that substitution reaction. All right, and so let's be clear here about what carbons came from what. I had these 3 carbons that were originally in my alcohol. That made up these 3 over here. And then I had these 3 carbons from my alkyl halide that made up those 3 there, all right? So in this case, it wouldn't matter which alcohol, like there's only sort of one combination of alcohol and alkyl halide that you could choose to get this symmetric ether here, all right? But what if we wanted to produce something like this? An asymmetric ether. Oh, whoops, this is my product. All right, well, there'd be 2 ways to do this here. You could either start, let's just color these again. There's this half and this half. You could either start with that tert butanol as our alcohol. All right, again, we're always going to first treat these with sodium hydride. And then our nucleophile, or rather our alkyl halide that we could use, is just that bromomethane. All right, so either my orange fragment can be my alcohol, and my green fragment my alkyl halide. Or I could have chopped it up differently. And I could have said, all right, I want that green fragment, that 1 carbon fragment to be my alcohol. We're going to treat that with sodium hydride. And then the other fragment, that bigger chunk, will make our alkyl halide here. All right, so in theory, we got 2 different ways that we could produce this particular ether here. Remember, when we were talking about Grignards and we had 2 different ways, we were like, we don't care. Either one will work just as well, all right? That is not the case here. One of these is very much so more preferred than the other method. All right? And the key here is we need to look at our alkyl halide. Remember when we talked about alkyl halides, we had said different alkyl halides have different propensities to undergo substitution reactions versus the flip side, versus the elimination reactions. Well, which one of these is more likely to undergo substitution with our alkoxide ion? The small one or the big bulky one? The small one, because that carbon is just way more accessible. So you're going to have a way more efficient substitution reaction. If we try to do this bottom one down here, we really wouldn't get any substitution product at all. We would get a bunch of elimination product. All right, so bottom line is we're not going to choose this method here. We only got one way to make these asymmetric ethers, and we want that more accessible fragment to be our alkyl halide. All right. All right, cool. So then for practice here, I want you all to tell me we're going to treat some alcohol with sodium hydride. And then we're going to mix in some alkyl halide. Now I want you to tell me which half is which if we're trying to produce the following ether. All right, so we got our asymmetric ether here. All right, and we can cut it up in one of two ways. We can either make it so the orange fragment is our alcohol and the green fragment is our alkyl halide. You'll see that in theory, you could use any alkyl halide. The bromines work really well in terms of like their effectiveness as well as the cost of them. So anyways, you'll see it default to a bromide. We're going to choose alkyl bromides here. All right, or I could have done the exact opposite and instead had the orange fragment, or rather the green fragment, be my alcohol. And the orange fragment be my alkyl halide. All right. Cool. So which one of these is correct? The method on top or the method on the bottom? All right, cool. So both of these are 4 carbon fragments, right? It's not a size argument, it's the accessibility. If we look, what would we classify this alkyl halide as? Primary, secondary, or tertiary? Primary. And what about this one? Primary, secondary, or tertiary? Secondary. And which one is more likely to undergo substitution reactions? That primary alkyl halide, right? So this top method here is going to be our preferred Williamson ether synthesis method for creating this asymmetric ether here, right? Again, we want our more accessible carbon to be on our alkyl halide so that our nucleophile can efficiently undergo this substitution reaction. Cool? All right, so that's how we make ethers. Now we're going to talk about how to break them. All right, how do we decompose an ether? Okay, so if we take our ether, and I'm just realizing now I forgot a very important part about our nomenclature of ethers, which is this guy right here has a very special name, all right? This is the ether that you will encounter 99.9% of times that you encounter ether. If we were to do the common name of this ether, what would this be? Everybody take a second. Give me the common name of this ether right here. All right, this is where we're going to chop it at this oxygen. We're going to jump on the one side. What would we call that alkyl group? An ethyl group. And then we're going to jump to the other side. What would we call that alkyl group? Also an ethyl group. And we got 2 of them, so instead of saying ethyl ether, we're going to say diethyl ether. All right, diethyl ether is, I think, maybe quite literally, I don't want to say only one, but yeah, 99.9% of the time that I've ever encountered an ether in the lab, it has been this specific ether here, okay, diethyl ether. So much so that this thing has a special name. They just call it ether. All right, if you're ever reading a protocol and it says blah, 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 ether, and you're like, what the hell, that's not a molecule, it's a class of molecules. They're talking about this specific ether right here, diethyl ether. It is just the most common one that you're going to encounter. Cool, so I guess we should go up here and just say, kind of like we made a note for other things that had special names. We got a special name here. That's our diethyl ether example. Again, so special, they just call it ether. All right, again, it's a good like non-polar, or at least slightly, just barely on the polar end of the non-polar spectrum. It's also got like a super low boiling point, so it's very easy to get rid of by just heating it up to, 35 degrees, 38 degrees, something like that. So very common choice for solvent in the lab. All right, anyways, back to what we're regularly scheduled programming here. Ether decomposition. So if we take an ether and we treat it with some of our hydrohalogen here, right? Our strong acids are hydrogen bound to one of our halogens, chlorine, bromine, or iodine. And what we'll see is quite literally the exact opposite of our Williamson ether synthesis. This is going to crack this thing in half, producing an alcohol and an alkyl halide. All right, so our ether decomposition, we're going to take our ether, treat it with one of those hydrohalogen acids to produce an alcohol and an alkyl halide. All right, we don't spend a ton of time diving into like the mechanism details of our reaction here, but we are going to look at this one a little bit more closely because it's going to help us better understand this reaction. All right. What happens in this reaction is first that strong acid is going to protonate this oxygen right here. Right? So it's such a strong acid. You know, acids are proton donors, and that sounds like this very nice, like, oh, here, have a proton, please, kind of deal. Well, strong acids are like violently donating, right? They're sticking hydrogens anywhere that they can put them. So one of those strong acids like HBr is going to be sticking hydrogens all over the place. That oxygen is going to accept that hydrogen. And what do we know about an oxygen with 3 bonds here? How many lone pairs should this have? Just one. And what about the formal charge on that oxygen with its 3 bonds and 1 lone pair? Positive. So, not super duper stable here. This thing is not very happy right now, okay? So now our hydrohalogen has lost its hydrogen, so now it's just that Br with the minus sign. All right, and what happens is that bromine attacks one of those carbons, breaking that carbon-oxygen bond. All right, so that's how we get on the other side our alcohol and our alkyl halide, our alkyl bromide here. Okay. Cool. So in this particular example, we started out with this symmetric ether. So my alcohol had 2 carbons, my alkyl halide had 2 carbons. All right. But now we're going to go to a similar problem here. What if instead I started out with this guy? All right. And I'm going to treat this with HBr. Okay, well, just like before, we could have 2 possible outcomes here based on what we've discussed. Either that orange fragment is my alcohol, and that green fragment is my alkyl halide, or vice versa. Right, or that orange fragment's my alkyl halide, and the green fragment is my alcohol. All right, right, well again, we're going to have one of these two is going to be our actual product and the other one we're not going to see at all. All right, so let's see if we can't figure out what's what based again on the details of this reaction. All right, so again, step one is going to be to protonate that oxygen, get it all super mad. And then we got our bromide ion. And that bromide ion is going to attack in order to form our alkyl halide. But it can either attack on this side or it can attack on this side. Which one of those carbons is that bromide going to have an easier time attacking? The orange one or the green one? The green one, right? So literally the exact opposite of our Williamson ether synthesis. We're going to have a preference for one of these or the other. And the more accessible carbon is again going to be our alkyl halide. Whoops. All right, so we're going to note here. Let's just say our halogen will attack. Again, that more accessible carbon. All right, so if we were going to make this alcohol here, or this ether here, we talked about how to do so using this Williamson ether synthesis. Now I want you to tell me what's going to happen if we were to treat this thing with our hydrohalogen. Let's just use a different one for fun here. We're going to use hydroiodic acid. Super strong acid. So again, that iodide ion is going to attack that more accessible carbon, which means that my alkyl halide will be the green fragment and my alcohol will be the orange fragment. Okay? So again, this is the exact opposite of our Williamson ether synthesis, or rather the exact reverse. If we took that alcohol and that alkyl halide and instead combined them after treating the alcohol with sodium hydride, we would get the other, we would get our ether product. Cool. All right, we're going to call it there. We will start in, or we'll keep epoxides as kind of a separate topic. We'll start in on that next lecture. Cool. Your exam